Rooftop HVAC systems. In this presentation, we're going to be looking at the sections of a rooftop HVAC unit, its operation, some special considerations, and then finally, a look at makeup air units, which are a common form of rooftop air handling unit. This is an example or in two pictures of rooftop units. They're self-contained boxes with everything required to provide heating, cooling, and ventilation on top or beside a building. The rooftop unit can be separated into two sections, the heating section and the cooling section. In the heating section, of course, we have burners, heat exchangers, and the mechanical and electrical components are similar, if not identical, to those found in mid and high efficiency heating systems. The heat exchanger will have the same types of devices also as what are seen in the typical domestic type of forced air heating systems. The cooling section is essentially an air conditioner with the same types of equipment and control devices. The heating sequence of operation is the same as what we've seen in mid and high efficient forced air furnaces and boilers. The cooling sequence is the same as an air conditioner. When we look at the components, they look largely the same, if not a little bit bigger in size. The heat exchanger will be larger because typically a rooftop unit is providing much more heating and much more cooling than a typical domestic furnace. Often all of the controls and many of the terminations are found on a side panel beside the HVAC unit itself. It's important to remember when we're looking at a system like this that they have four separate motors: an outdoor fan motor, a compressor, an indoor fan blower motor, and an induced draft fan. So let's take a look at that rooftop unit again and see where these are all located. The main blower motor at times is connected with a drive belt to the main blower fan. The combustion fan is located near the burner assembly. The compressor is used to compress the refrigerant, and it has to do with the cooling system. And finally, the condenser fans blow air across the condenser coil to remove heat from the AC system. If we look at the system as more of a simplified diagram, we can follow some of the airflow. What's interesting about a rooftop unit is that there are automated louvers typically, and the louvers will control how much fresh air is brought into the building and how much return air is utilized. A louver is essentially an automated controlling set of Venetian blinds, which allows either a restriction or an increase in the airflow through them. When we look at the heat exchangers, there are three. There's one heat exchanger for the heating assembly to create increased heat levels for the air traveling into the building. There is also two heat exchangers or coils for the air conditioning system. The evaporator coil, just like in a standard AC system, is going to get very cold when cooling is required and air flowing through it will be chilled. The condensing coil is located outside, and its prime purpose is to have heat dumped out into the air from the refrigerant that flows in it. At any given moment, a rooftop unit will only be cooling or heating, never both. Let's take a look at a rooftop unit that is operating in a fan-only stage. This means that there is only air being blown throughout the facility and there's nothing else happening. The louver for the outside air is closed, and the air is simply circulating from inside and outside, not being cooled or heated. When we go to a fresh air louver open, it means that we're now mixing some of the fresh air from outside with the return air inside the building. When we look at a heating cycle, only the heat exchanger is being utilized and the heating components that would be required for that section. The combustion air blower and different types of rollout and temperature sensing devices. If we were to look at cooling, that's when the air conditioning is turned on. The refrigerant motor compressor energizes, the evaporator coil is then chilled, and the air that flows through it is cooled. On the other side, the condensing coil then starts to have refrigerant flow through it that is warm, and there is a condensing fan that draws air from outside through the condensing coil to remove that excess BTUs of heat energy and dump them outside. At times, we can also take advantage of the difference of temperature outside than inside. Sometimes we need cooling in an area of a building when it is cold outside. Examples of that would be things where there are large numbers of people or computer server rooms. A computer server room generates a significant amount of heat, and when it's cool outside, we may still need cool air blown into that particular room. In order to save money, at times the HVAC rooftop unit can be set up so that the exterior fresh air louver is wide open and the return air is closed. And that brings in cool air from outside and dumps it into the room that requires cooling without utilizing more electricity for the air conditioning compressor system. Let's look at some special considerations when it comes to rooftop units. First off, we know there needs to be an isolating switch or disconnect, according to 28604 subrule 5, and it must be within sight and within 3 meters of the equipment. Often it's mounted right onto the rooftop unit itself. There is also a secondary item that is required, and that is a 520R T-slot 20 amp receptacle from 26710, and that's to facilitate maintenance from all of the different trades that may have to work on the rooftop unit. These large heating units sometimes have double stages of heating or cooling. And the difference is that when there is a small difference between the set point and the actual temperature, only one of the heating stages will initiate. If there is a large difference between the set point and the actual temperature, then both of the heating sections would come online. And in this way, it's a slightly more efficient use of a large heating system. Let's look at a couple of rooftop wiring diagrams. Like most rooftop and HVAC diagrams in general, they're not specifically a schematic or a wiring diagram and are of limited use unless we know the sequence of operation that should occur when we're encountering a trouble call for heat or ventilation or air conditioning. Primarily, what these diagrams provide us with is simply the wiring termination locations on the equipment for the various types of control devices. Makeup air units. A makeup air unit is used to make up the air loss from a building due to exhausting requirements. Makeup air units turn on when the exhaust systems are on, and we looked at a version of this briefly when we were discussing interlocking with a standard domestic furnace. In larger applications, makeup air is used in laboratories when significant fumes have to be evacuated out of the room. Large quantities of air have to be then brought in. When we're doing welding in welding shops, a lot of the fumes from welding is then siphoned out through snorkels, which means significant air must be then brought into the same room. Kitchen facilities in restaurants and fast food. There are large exhaust fume hoods which suck all of the combustion gases out above the grill, which means significant air must be brought into the kitchen area to avoid, in all of these situations, a negative air pressure in the building. Spray booths and lots of different types of finishing applications where there's significant exhausting of fumes. And finally, underground parking garages, where exhaust fans will be turned on when carbon monoxide levels are sensed to be too high or at regular hourly intervals. When the air is sucked out, more fresh air needs to be brought in. Keeping this in mind, there are then two different types of makeup air systems: direct fired, which has no heat exchanger, and indirect fired, means a heat exchanger is used. Let's look at direct fired first. A direct fired makeup air unit is used in restaurants typically above cooking grills. And this is really just areas that we're not concerned with the air quality because the supply of this made up air is usually right in front of the exhaust hood. In this way, particles of combustion from the actual burning natural gas do actually go into the room because if it's a cold day, we need to heat the air. Once it comes in, it immediately gets sucked back out through the kitchen hood along with all of the combustion gases from the grill. These are really only used where we're not concerned with the quality of the air that's getting dumped into the building. By contrast, indirect fired will be utilized in areas where we need air quality levels to be maintained. So many applications use indirect fired makeup air systems. Again, the purpose of this is not only to make up the air that goes into the building, but to preheat it so that we don't have extremely cold air going into a building during winter and causing other problems with the uh, temperature inside the building. Here's an example of a horizontal mounted makeup air system and another one. They come in many shapes and sizes, and some of them are not even on the roof, they're so large. This is an example from another installation, which was a assembly plant which had a hazardous spray onto an item of manufacturing that went on a conveyor system that hung from the ceiling. Over here would be the exhausting filters that would have sucked all of the spray particulate out after it had left the gun, anything that didn't actually adhere to the object that they were spraying. It would then be controlled and interlocked with a makeup air system through pressure switches. Once the makeup air system was confirmed to be operating, the exhaust system would then turn on. This is the size of the makeup air system, which was humongous, considering the amount of gas that had to be brought in order to create enough heat. This is a 2-inch diameter natural gas line to preheat the air before it gets dumped into the building. This is another example of a laboratory makeup air system, and in this case, a slightly different proving mechanism was used to confirm that the makeup air was operational. In the previous one, we used pressure switches. In this one, a little bit different, but this is a CT. And the CT is measuring the current that the motor wire will have drawn on it when the makeup air fan is running. When the CT senses that enough current is flowing, it confirms that the blower motor is operational, and that then is allowed to interlock with the exhaust system to allow it to turn on. Typically, the makeup air must be confirmed as operational before the exhaust can start to take place. Finally, large HVAC installations with all of the different things that we have looked at are typically in a form of digital control for the operation of all of the heating and cooling and dampers and humidity and fire alarm interlock and fresh air introduction. There are a lot of moving parts. And because of that, the introduction of programmable logic controllers has become quite common. When we're discussing programmable logic controllers with HVAC, they're typically referred to as digital controllers. They have inputs and outputs, discrete and analog, but they're specially designed for the application of HVAC. Here are some example snapshots from a user manual when it comes to connecting different types of control contacts as well as different sensors back to a DDC controller. The logic used and the form of a DDC controller is different than a PLC, and even the programming and the operation of a system will differ significantly. DDC controllers have pre-built programs for most types of heating and ventilating applications, and it's typically up to the user then to simply select what is required and connect the necessary items. Now, there are many, many names, and you certainly do not have to memorize these, but as you go through your travels as a journeyman electrician, you may encounter these, and they are in relation to an HVAC controller. DDC, EMS, BAS, ECS, and FMS are all acronyms used commonly with digital HVAC controllers.